does process a lot of the starlight. Typically, in a typical galaxy, about 1/3 of the starlight is being absorbed by dust and reprocessed, re-emitted in the infrared. In very dusty galaxies, this can be more like 90% or so. And this means, so in this little SED plot that you see here, you see that the light from the stars is actually somewhat diminished, and there is a lot of output in the infrared and the far infrared. This means that the overall interstellar radiation field within the galaxy is getting a lot redder, and this, of course, changes the drivers of galaxy evolution. Then another important reason is that dust is actually necessary catalyst for forming molecules. Molecules form on the surface of dust, and these molecules are necessary to actually have star formation proceed, as they provide cooling mechanisms during the collapse of stars. So that's another reason that we want to study the formation, evolution, and the occurrence of dust. And then finally, and this is a reason that is quite important for our talk, the topic that we'll be talking about today, is that interstellar dust masses are measured throughout the universe. It's quite an easy thing to measure, or so it seems. And they are used as proxies for interstellar gas masses if you don't have any other measurements available for galaxies, and therefore for star formation rates. And in this sort of step of proxies, you basically have conversion factors that you apply between dust masses to get to gas masses and to get to star formation rates. So how do we measure these dust masses? Well, there are three important regimes here. One is the optical and the UV regime, where you can study the dust in absorption. And you can measure the mass of dust, particularly in its interstellar medium, along this line of sight towards a background source. So for instance, using the interstellar extinction curve here, you can look at the reddening of stars in the solar neighborhood and beyond, to construct a dust mass map like the one here on the right, which is constructed using Gaia data. If you go to the mid-infrared, you have to start doing more complex modeling because dust both absorbs and emits at these wavelengths, but especially when it's warm, and you have to do full radiative transfer modeling. So this is particularly important for circumstellar dust that is quite hot, that is just recently being formed. And for this purpose, we use dust opacities. Here are some example curves. It's a fairly old plot, but it gets the idea across. I couldn't get I couldn't find a nice looking plot that is more recent. So the actual values in here may be not the most current anymore, but this is sort of the kind of opacities, as you can use my pointer here. These are the kind of opacities that you're using. So you have this, so here you have kappa, and the opacity falls off with wavelength here, and you clearly see the silicate features. Now, if you model this for instance, an AGB star with a very dense, dusty shell, you see here what happens to the spectral energy distribution of the AGB star, that the star here is extinguished on this side. You see the silicate features in absorption because it's a high optical depth still at this wavelength, but then at the longer wavelengths, you're having thermal dust emission due to this tail here. This is just an example. Then, if you are actually looking at a far infrared submillimeter millimeter regime, you still have this cold dust component that is emitting here. So you can look at the colder dust in a circumstellar environment, and also interstellar medium dust. And basically, you're approximating the dust masses by solving for this formula here, where kappa is basically an approximation here of the slope, and you no longer worry about all the substructure here. because it's the dust is so cold that the black body emission at those wavelengths is negligible. So you just have a very smooth curve like this one here. I will come back to this later, but these are different representations of kappa for different beta values. We'll come back to this later, but you can see that it's just a smooth curve. Okay, so then the life cycle of dust in galaxies is sort of the context that we're doing this all in. So you have the interstellar dust here in the galaxy, out of which stars form, and you have two regimes. You have the massive stars and the lower mass stars. The massive stars, of course, evolve fast into the supernova phase, where you can form compact objects here, but the ejecta end up in the interstellar dust reservoir again, enriching it with the product of nucleosynthesis. On the other side, you have the lower mass stars that are cooler, that have a more gentle path of evolution and emit or eject their masses in a more gradual way. And actually, these kind of stars, the HB stars, are thought to be the main producers of dust in galaxies. Again, here you also form compact objects, white dwarfs in this case, but the stellar ejecta replenish the ISM again with the products of nucleosynthesis and dust embedded in them. So we actually looked at this for the Magellanic Clouds in a lot of detail with the SAGE and Heritage projects, which were carried out on Spitzer and Herschel. And we did both imaging and spectroscopy surveys, but here I will focus on the imaging surveys. So we mapped the entire LMC here and SMC in all IRAC bands, 3.6, 4.5, 5.8, and 8 micron, and all MIPS bands, 24, 70, and 160 micron, and also most of the bands available in Herschel, 100, 160, 250, 500, I should say, I think, or is it 450? I don't remember now. 500, I think. It's a typo. So this map here is 7 by 7 degrees. This is an enormous map that we made. We find 8 million point sources in this map in the 3.6 micron image. At longer wavelengths, there are fewer point sources because the stars get fainter. The metallicity of the LMC is about half solar, and it's at a distance of 50 kiloparsecs. Here we have, this map is somewhat smaller. It's of the order of, I think, 3 by 5 degrees. And we have 2.5 million point sources in here. The metallicity is 0.2 solar metallicity. And we have, the SMC is bound at a distance of 60 kiloparsecs. So just to give you some context. So what we did was we looked at the production of dust in the Magellanic Clouds. And you can do this by constructing a grid of spectral energy distributions, like I showed you before, where you are modeling the dust emission coming from an AGB star. And we have two different chemistries here. We have the oxygen-rich chemistry here and the carbon-rich chemistry here. Carbon-rich is coded red, where we have varies the important parameters of the mass loss, such as mass loss rate and the size of the shell, etc., and also the composition. And we made a grid. So here is actually the grid of models for which we then calculated the fluxes. So here you can see what a typical grid point, the spectrum of a typical grid point looks like, and you can of course calculate synthetic photometry from that. And from this synthetic photometry, you can make diagrams 8 versus 3.6 minus 8, and you see the coverage. It's not very clear, I'm afraid, but the coverage of the grid is shown here, and here for the oxygen-rich case. And then we compare with actually the sources in our catalog, and those are the colored points here and here, and we find the nearest grid points for all of the sources in the catalog, and which were millions of sources. And then by adding up all these mass loss rates that correspond to each grid point, we actually can calculate the total dust production rate in the LMC and in the SMC. And here are the numbers that we derive. And it all depends on the model that we used here, of course. Huh? So don't worry too much about these models, but the total is a few times 10 to the minus 5 solar masses per year that's being produced by evolved stars in the LMC. And in the SMC, the total dust production is found to be a factor of 15 lower. Now, then we can actually compare this to the interstellar dust masses in the Magellanic Clouds, because the idea is that these HGB stars are producing this material that is being injected into the interstellar medium. So you have to build up your interstellar dust reservoir over time. So this is a map using the Herschel data and the MIPS data, and we calculated the interstellar dust mass on a point-by-point basis by just fitting these simple modified black bodies at each data point. And in doing so, you can derive a total dust mass of about 7 times 10 to the 5 solar masses. Recall that the dust production rate is a few times 10 to the minus 5 solar masses per year. And this means that the replenishment time scale, so in other words, the time that it takes to produce the entire amount of dust in the interstellar medium of the Milky Way, the LMC, is a few times 10 to the 10 years, which is just about corresponds to, well, the age of the LMC and the age of the universe itself, of course. So it's very tight fit here. If we then start looking at the star formation rate, so we can actually do the same game that we did with the evolved stars, also with YSOs, with young stars, fit them to spectral energy distributions and kind of calculate the consumption of dust from the interstellar medium. We actually find that it's consuming dust at a somewhat higher rate of 8 times 10 to the minus 4 solar masses per year. And if you then assume a dust to gas ratio that is appropriate for the LMC, this is 0.38 solar masses per year for the star formation rate. This means that the amount of time that it takes to consume this dust in the interstellar medium is more of the order 10 to the 8 years. So it's way faster to consume the dust in the interstellar medium than to produce it. So we have a bit of a problem here. And then I should also say that what we didn't take into account here is the destruction of dust through supernova shocks and so on. So we assume that once the dust is formed, it remains there forever until it's being consumed by a star. And the formation of dust in the interstellar medium. So this, in the end, this might be an important component. You can also try to model it rather than taking an observational approach. And this was done, we did this actually in 2014, where we took the star formation history of the LMC, which was derived by Harris and Zaritsky in 2009, and used that along with stellar evolution models, theoretical dust yields of HGB stars, applied it over the entire star formation history, as I said, and then you can sort of predict a dust production yield for the HGB star, a theoretical dust production yield of all the HGB stars in the LMC. And here, this data point here in the end is the actual measurement that we have for the interstellar dust reservoir. So again, we just about get there with this range. This green band is the range of possible outcomes. And again, this doesn't take into account the destruction by supernova shocks If you use that, then your solution will be much lower. So we have a dust budget problem in the nearby universe, but it turns out we also have a dust budget problem at a higher redshift, and that's where actually this dust budget problem was first identified and named, because you have so much less time available to actually build up your interstellar dust reservoir. So what happened was that in about 20 years ago already, there were observations like this one of distant galaxies at redshift 6 and higher, which were fairly dusty, 10 to the 8, 10 to the 9 solar masses of dust. And the kind of observations were done to determine that it's like this. So these are submillimeter volumetry observations, and you just have a few detections here, and dust SED is fitted, and a dust mass is derived. Now, this amount of dust, 10 to the 8, 10 to the 9 solar masses of dust, it cannot really be explained with stellar dust sources. So this was first identified by Morgan and Edmonds in 2003 already, sort of in the same year, where they tried to do calculations, and you simply do not have enough time to have HB stars evolve within the first billion years after the Big Bang. So if you include supernovae as well, your situation gets a bit better, but you have to have very efficient dust production in supernovae and none of the destruction actually to get sufficiently high, but then still you're about an order of magnitude away. Well, at this point, actually, this is what matters from what has been observed. So this is a real problem. It persists to this day. And I want to talk about this a little bit more. And first, we're going to talk a little bit about the opacities again to figure out where this problem might be coming from. So these dust mass determinations, they typically fit an SED with a modified black body, where the black body is multiplied by opacity, which is just simply a power law of a kappa naught times a lambda over lambda naught to the power minus beta. And a single, or perhaps at best a few temperature components are fitted in these SEDs. So the problem lies in part that of all the kappa values that could have been used, actually, so the kappa 500 is a typical reference, that's 500 micron reference wavelength. The one that is very often used here is James et al. 2002. And Drain et al. 2003, 2007. So here the red one and the two orange ones. And as you can see, they are sort of on the low end of all the kappa values that have been mentioned in the literature. And these are different sources for kappa. These are theoretical calculations. These are laboratory measurements. These are observationally derived kappa values, all these different things. But the ones that are commonly used, perhaps because they're nicely tabulated, are on the low end of this. So if you use these, you're going to have a much higher dust mass to explain the same amount of emission. So that's already a problem. Then another problem is actually that the kappa is, the measurements are only used at a single wavelength, 500 micron. And then beyond that, using this power law, actually a beta is simply fitted often, and rather than referring back to the full tabulated values, and this means that actually your dust masses may vary greatly as well. Here this plot shows that quite nicely. So beta is typically between 0 and 3, and you see that so these are all normalized at 1.3 millimeter. And you see that the fluxes that you might measure at 450 and 850 micron vary greatly for a dust mass that is the same in all these cases, and the temperature is the same in all these cases. It's just the beta that is changing. And of course, for dust species, if this dust species are well characterized, we shouldn't be fitting the beta. It should be actually something that is known. And here, what has happened here, I include this just for illustration, is that you actually, if you start fitting sort of point by point within a galaxy, so here this is Andromeda, you see that the beta is different in different parts, or you get a different beta out of the fit in different parts of the galaxy if you do this fit by fit, or this point by point analysis. Okay, so when I talk about the fitting of these SEDs, what is it that we're actually talking about? So here is an example from 2007. This is up to 20. This galaxy is rather well sampled, so you have maybe a dozen or so photometry points here, so you can make a reasonably good fit. But in some cases, the number of photometry points that have been fitted is very small, just 5, 4, 3 photometry points for 3 parameters, right? In one case that I know of, in 2015, a single photometry point was fitted. So they just assumed a beta, they assumed a temperature. And of course, then, yes, you produce a dust mask, but what is the meaning of this, right? I mean, together with my group, I started a bit of a program into looking into sort of systematic effects that we're seeing in these dust mass determinations. And one of the first things that we looked at was, rather than using this power law opacity, look at some more realistic opacities that actually are measured in the lab. And I proposed this because I already knew, and this has been known for some time here, since the late 90s, that these dust opacities at these long wavelengths actually are not constant, they are temperature dependent. So it's the opacities themselves that are temperature dependent. So what you can see here, this is amorphous carbon. You can see that at the lowest temperatures, it has this particular slope, but at higher temperatures, the slope is becoming shallower and the flux or the opacities are going up. We see the same behavior for silicates here, here, and here. In principle, these are some different kinds of silicates that might be typical for what we see in galaxies. And for reference, this plot here, this line here, shows the James et al. Opacity power law. So this is what people typically use to fit a galaxy SED. So you see this difference here, and you could imagine this line here as well. It's really quite a big difference with what is used. So we constructed a typical grain mixture using these lab opacities that I just showed you at 2 different temperatures, at a 100 Kelvin and a 30 Kelvin, of a mixture of carbon-rich and silicate dust. I believe it was 30% carbon and 70% silicate. And then you get these 2 lines. So this temperature dependence is still there. And these various lines here, again, are typical power laws that people have used in various studies. Here again is the James et al. Value, which is very commonly used. So what we first did is we took our opacities and we made a grid of synthetic galaxies, which is basically a cloud of dust at a single temperature. And we did this at different temperatures, and then we placed this galaxy, this cloud of dust, at different redshifts. Then what we did is we extracted synthetic photometry at some commonly used photometric bands, and we fitted that synthetic photometry using the commonly used methods in order to derive a dust mass and a temperature as well. So we have a fitted dust mass over a real dust mass, the dust mass that we put in. And here is the temperature of the real dust mass. So we did this for different temperatures. And what you can see is that for different, actually the pattern is more or less the same. no matter what redshift you're looking at, you're basically overestimating the dust mass by a factor of 10 to 20 by doing this. Yeah? So this is really quite significant. What we then did was we actually made a synthetic galaxy that had a more complex temperature structure. It had 2 temperature components. So this is slightly more realistic. We had 2 temperature components, one of 100 Kelvin and one of 30 Kelvin. And where we had different fractions of warm dust to the total dust mass. So we also varied that. So that is shown here on the horizontal axis. So it goes from very low warm dust components to almost, well, about half of the dust being in the warm dust component. And then you can calculate, so you get these black curves here. Those are the calculated SEDs. You can work out the synthetic photometry for that. And then we fit, with the red curve, a single temperature component. And from that, we then derive the masses again in what is commonly used. And you see that, interestingly, the differences are not so great now. It's only a factor of 5. Here, it's actually really close to the reality. So obviously, this is something to look into more. And we're currently in the process of making a larger model grid and trying more combinations. But this is where we stand so far with this. Another thing to consider is that especially when you look at these distant galaxies, is that you're looking at an entire galaxy at once. So you're having a bit of the same effect that we had before, where you're looking at the entire dust population all at once. So you see all these dust temperatures mixed together. Now, the question is whether you can actually investigate that, split up these dust populations, and try to see if you fit smaller subsets of the dust at the same time and add up the total if you still get the total dust mass. So that's another way of figuring out whether a single temperature fit is a good way of doing this. And here is a strip. This is a strip in the LMC, just part of the LMC. Again, this is actually the Heritage Survey, where we have, well, I was not involved in the study actually, where my colleagues have combined pixels together. So this is the original resolution, and then we just start combining pixels together to ultimately a galaxy, the whole strip was combined together, and repeat the procedure of determining the dust masses on a pixel by pixel basis and adding up the dust masses that were derived for each pixel to see what the pattern was that was found. And it was found that if you set the dust mass that you find by integrating everything together and analyzing this result to 1, that if you go to smaller and smaller scales, that you find larger and larger dust masses until you're about 40 to 50% above the original. So there is some effect here that if you start splitting out these components, so you're resolving your galaxy, you start seeing more dust because you are not lumping all the temperatures together. You're maybe resolving star forming regions, and this is because, of course, the emission is so strongly temperature dependent that it matters if you sort of separate out the star forming regions from the rest of the dust. So this is something that we're going to look in further. We're currently working on this together with master student Gemma Domenech here. And so stay tuned on more updates on this. Now, going back to evolve stars and also closer to home, I want to highlight another project that we're working on called the Nearby Evolved Star Survey, NESS. And what NESS does, this is a survey done with the JCMT, is that it is doing a volume complete sample of nearby mass losing AGB stars, where the completeness distance depends on the mass loss rate bin. So here's a diagram showing that. So the lowest mass loss rate bins are complete to the nearest distance, and the higher massless rate things have a completeness to further distances. And then we did observations with the JCMT, predominantly more than 1,000 hours, actually more of the order of 1,400 hours, is still ongoing, in fact. And other radio telescopes to get submillimeter continuum measurements and CO line fluxes. And we also have mapping observations for a subsample, and that is those are the ones here in the black squares. So the key questions that the NESS survey wants to address is, well, basically we're coupling back to this question about the life cycle. We want to study what the production is of gas and dust in the solar neighborhood into the ISM. And we think that you need a volume complete sample for that. Then other questions include a study into the gas to dust ratio in stellar outflows, looking at the mass loss history because we have spatially resolved observations. We also want to constrain submillimeter dust properties, and that's important in the context of what I'm talking about today. Tracing nuclear synthesis processes is something that we want to do, looking at the 13CO to 12CO ratios. Ultimately, we want to extrapolate what we find in this nearest few kiloparsecs to a galactic dust production rate. And we think that some of the observations will be suitable to detect deviations from spherical symmetry. We have observations, submillimeter continuum observations like this one that's already published. This is actually from an object with a detached shell, and you can clearly see the extended emission here. And also in CO, you can see that the line profile, the CO line profile, varies a lot from point to point in the outflow, so we can do some interesting science with that. And also CO line emission gives you another measure for the mass loss rate, which you can plot here and compare with the dust production rate. And you hope that you get a close relation here, which feeds back to the gas to dust ratio. So those are sort of the key questions that we are addressing. But for the purpose of this talk, I want to talk about the anomalous cold dust reservoir that we have started to see. So this was first detected in a pilot study that we did in 2018. Tavisha Dharmawardena is my PhD student, former PhD student, and she looked at a sample of about 15 HB stars and basically fitted as a function of radius the temperature, the density, and beta, so just what I explained before. And she found that at a certain distance, there was an overestimation here of the density compared to what was predicted, just from having a constant mass loss rate. And this was really quite systematic. And what this means is that if you look at this this plot that I showed you before of the spectral energy distribution of an AGB star, that so actually this one, it has 2 submillimeter points in here which fall nicely on the extrapolation from the mid-infrared, but this is not typical. A more typical case is that the emission actually is a factor of a few above what you would predict from the mid-infrared opacities, the mid-infrared modeling, assuming a constant mass loss rate. So in other words, if you look at the whole sample or part of the sample that we've published so far, you see that the excess at 850 micron for the objects with different mass loss rates is, well, here is 1. So for low mass loss rate stars, we don't really see that much of an excess, or maybe on average it's a little bit high, but for the whole sample, we see a factor of a few up to a factor of 10 excess emission at 850 compared to the predictions based on the opacities and the assumption of constant mass loss rate. Now you could say, well, perhaps we don't have constant mass loss rate, right? But that's where it is important that we're looking at a sample, because if the mass loss rate goes up and down, then you would also be scattering around 1 here and not be systematically above 1. So I think this is really a significant result. And we're currently working also on doing this for the entire sample and actually reverse engineer what kind of opacities we really need at 415, 850 micron to match with the mid-infrared opacities to actually accurately predict those fluxes at those wavelengths. So, yeah, and then I want to highlight this study. This is still very much ongoing. Hashtag a survey of Andromeda, also with JCMG. This, of course, well, is the nearest, one of the nearest, two nearest spiral galaxies, and we can combine this survey that we will ultimately get that maps the entire galaxy with Herschel data and do more detailed analysis, especially at these longer wavelengths, to find out if we see the same sort of behavior here. We can also then combine this with dust production rates that can be estimated using existing infrared data, for instance, WaveCam on Burkert. But this can actually be greatly improved upon by JWST, although it will be quite a task to map the entire thing with JWST. So, coming up to the end of the talk, so what is the current picture that we have now? This is very much work still in progress, but what I think is going on with the dust opacity is that dust opacities are not well characterized at far infrared submillimeter wavelengths. And there is no reason to believe that the locally derived Train and Lee opacities or other locally derived opacities apply throughout the universe, right? And next, there are systematic effects that play a role in dust mass determinations due to limited information that we have on the photometry, limited number of bands, and also limited spatial resolution. We are forced more or less to apply single temperature fits, and these just cause systematic effects that we're trying to evaluate at the moment. That's what I'm saying here. The quantification, the combination of these effects is still ongoing, but the initial indications are that we are overestimating the dust mass by a factor of about 10 using the current methodology of measuring dust masses. Now, what would be the implications of this, especially at higher redshift, where you have galaxies where you can only measure far infrared submillimeter, millimeter, centimeter wave broadband fluxes because it just takes too much time to do other things. So this is in particular deep field surveys and so on at these wavelengths. Well, what it means is that if all you have are these far infrared submillimeter photometry fluxes and you're overestimating the dust mass, you might be overestimating the gas mass and ultimately overestimating the star formation rate. And this has potentially far-reaching consequences for our view on galaxy evolution, especially in the early universe. So this is something to keep in mind in those kind of studies. So to wrap up, so we are making progress towards characterizing dust masses in different parts of the dust life cycle in galaxies. We're looking at the Magellanic Clouds, Andromeda, solar neighborhoods. They all provide at least a partial picture, or in case of the LMC, a pretty complete picture. However, we think that the interstellar dust masses, both in the nearby universe and in the distant universe, that are determined at far and infrared submillimeter wavelengths are inaccurate. There are degeneracy with temperatures and this beta. Spatial resolution affects the dust mass determinations. Opacities may be severely underestimated, and these effects are seen both in a nearby universe and at high redshift. And this leads, in my estimation, to an overestimation of interstellar dust masses, and therefore potential for overestimation of star formation rates with implications for galaxy evolution. Thank you.
With the energy distances, one thing I did not understand when you showed on different colors, dust production rate, I understood.
This one?
Yes, this one.
Okay. So we determined the dust production rate, because we actually the sample has been selected based on infrared observations. So we combine a couple of all sky infrared observations, which is a challenge in itself, because they're so vastly different. And but then you basically have an SCD. So we fitted the SCD of these galaxies, very similar to what we did in the Magellanic Clouds, and you can estimate. So we compared it against the same grid, basically, and you can determine a dust production rate. So yes, so then you have different things. Yeah.
What I don't understand is this ends up being a volume conflict.
Yeah.
Why there would be a relation between the dust production rate and the distance of the stars in respect to the sun?
No, there isn't. But we could have drawn the line here for everything, but then we would have just crowded this diagram with lots of low mass rate AGB stars, and we wanted to have a balance between. So high mass rate AGB stars are much rarer. Yes, so we have to go further out to get a decent sample. At the same time, they're brighter. So another issue here, actually, if you go to very distant with low mass rate AGB stars, is that you start confusing them with YSOs and other red objects. So we wanted to also be fairly sure that we were detecting AGB stars. So this is also some sort of confidence limit. But
then what is shown here, then it's not the volume complete.
It is, but it's per bin. So this blue bin is volume complete to here, the yellow bin is volume complete to there. Yeah. So it's some kind of wedding time. Yeah, different volumes for different mass rates. Yes.
At this point, to try to correct it with the systematic that you know that are out there in the production.
So we do the fit in the mid-infrared. So in the mid-infrared, we are quite confident of this dust production rate. So this is calibrated against the near and mid-infrared. Yes, yeah. So yes, the inaccuracies in the far infrared, they're not captured in this plot because the observations of that are not taken into account here.
What kind of how do you explain it?
So, well, I would be crossing over into a different field here. So yes, I was thinking if I could say something about the real implications of a reduction of the star formation rate, because it changes a lot of things. Of course, in the nearby universe, you have other measures to measure the star formation rate, not just the dust opacities, right? So maybe we should also look at the calibration between these different measures. I think I'm not qualified to say what the detailed implications would be of reduction of star formation rate. That is really crossing over into a different field. Yeah. So if anyone has any ideas about this, I would love to continue to discuss. Yeah.
So in the next one, the slide, I think when you show the outline one. Yeah.
This one?
Yeah, this one. So, okay. If I understand correctly, so here, then you have a time sequence, right? Because you have spatial resolve.
Exactly.
But why? So this idea that you are using constant mass loss right here, right? I mean, these are HU stars, so we know that they have thermal pulses, so they have some episodic mass.
Yeah, they do.
But there is kind of like a minimum mass loss rate which corresponds to the state where they are in the interface state. So I would not expect that all the mass loss rates you are estimating there, or the excesses, scattered around one. It seems to me natural that they are above one, right? Because one is your, let's say, basic mass loss rate, which corresponds to more or less the steady state of the HU star. And then you are piling up on that the shells, this excess emission, right? And they will push up always.
I guess that depends on the duration between the two phases, between the enhanced mass loss rate and the lower mass loss rate. Here, in this case, as you can see, if you want this to be a pulse, it's a very long duration, right? So a pulse would be much narrower. So I think yes, this is a valid concern, and I think we should look into this. Another argument, of course, would be that if this is then really long, and if this is really a pulse or an enhanced mass loss rate, then you might also, because it's so long, have quite a few AGB studies that are actually doing this right now. And then you would see a dip here, but we're not really seeing that. Yeah, so I think there is really a problem with the opacities here. Yeah.
Theoretically, the price should be much larger.
Yeah. So we do have some genuine examples of this. Actually, the other study that I showed here, this one, well, I don't show the radial profile, but it looks quite different. You can see this is a detached shell. You see a real clear, enhanced, an episodic, and it's narrow. Yes, absolutely.
Any other independent kind of measurements have bright galaxy, the gamma burst, the galaxies, for example, which you measure the amount of dust independently and compare.
Yeah, so that would be interesting to do as well. One of my collaborators works in the X-ray domain, and so far we've been looking at compositional differences, or because there are compositional differences. Actually, if you look in the X-ray spectrum, you see much more evidence, for instance, for crystallinity than you see in the infrared. So that is interesting as well. But if it would be possible to estimate dust masses using the X-ray domain, then we could use that as an independent calibrator. Yeah, that would be interesting. Yeah. Yes. Yeah. Yeah, so I fully agree with you. So I actually come from the astromineralogy background. So I started out with studying the composition of dust and documenting the differences from one environment to the next, right? And then to encounter, especially the studies at high redshift, where they just say, okay, we have 30% of carbon, 70% of silicates, and we just use standard opacities for both of them. It doesn't sit right with me, because I know from studying the nearby universe that there is a lot of variation from one place to another. So perhaps one thing that we could do is, when we do these parameter studies that I was talking about, is actually also use the composition as another parameter that we could vary and see what happens to the emission that we observe. That is one thing that we can do. We can also look at what simulations predict for the composition of the chemical composition of the interstellar medium, and adjust the prediction expectations for the dust composition accordingly. So if the interstellar medium is more oxygen rich or carbon rich, or has more or less of the important metals, then maybe we can try to adjust the composition as well. Yeah, and certainly an avenue for exploration in the future. Yeah.
You mentioned in the beginning that the AGV contribute most to the dust.
Yeah.
But when you show the high redshift, of course, that should come mostly from supernovae.
Yes. Yeah. So that statement was based on the local situation. Yeah.
So relating to Emily, is there a way then an AGV is also supernovae?
principle, yes, but we do not know enough about the properties of dust produced by supernovae. Yeah, we have relatively few supernovae that we have studied the composition, the dust composition of. So I think we cannot say enough about that. But in principle, yes, and the meteoritic record also suggests that there is a difference between and yeah. There is a lot of data in the infrared, but what is true is that there are not so many active labs anymore, so new measurements are not happening so much at the moment. As for the X-ray, I mentioned before my collaborator, so she was interested in the opacities for or the spectroscopy for crystalline silicates in the X-ray. There were no spectra available, so she just went out and measured them. Well, Sasha. Okay. Yes. So they went out to measure them. Yeah.
Okay.
Yes.